start with a second talk. So in the first talk I gave earlier, we discussed pragmatic reasoning while assuming that there is a shared, given lexicon that is shared across speakers and listeners in a given population. And in this talk, I would like to address the question of what principles underlie the emergence of a shared lexicon in interactive agents. So we'll relax the assumption that there is a shared lexicon. Instead, we'll ask how this lexicon may emerge. And to this end, we'll consider a similar communication model as before. So we have a speaker that tries to communicate some meaning M to a listener by producing a word W, and then the listener tries to guess the speaker's intended meaning. But here, we will not assume a shared lexicon, and so basically the speaker and listener needs to learn the lexicon or coordinate on a shared lexicon. And for simplicity, we'll think about the kind of speaker's production distribution as the lexicon, or as defining the lexicon, although we could have done the same with the listener. Okay, so one kind of very common and popular approach to this question comes from the machine learning literature and game theoretic approaches to language, and it argues that, or it typically assumes that a lexicon emerges from agents optimizing or trying to maximizing some utility function. So this approach seems very natural, right? We're trying to communicate in order to achieve things in the world, but it also has some limitations. For example, it is task specific, so it does not easily generalizes to other tasks. It often violates some properties that we know human languages have, so it sometimes violates linguistic universals. It's not particularly, it often leads to communication protocols that are not particularly human interpretable, and it could be very sensitive to the way we set up the environment. So it can be sensitive to the noise in the environment or things like that that don't necessarily or are not necessarily known to shape human languages. And so this alone seems to be kind of a limited approach. Another approach to this, or another view on this question is more often considered in the cognitive science literature, where we have increasing amount of evidence that human languages, and specifically the lexicon, is shaped by general communicative constraints or informational constraints. So this approach is task agnostic. It doesn't assume anything, it doesn't explicitly model the goals of communication, just the ability to communicate successfully, but it does have broad empirical support. In contrast to utility maximization, which usually comes with some specification of the dynamics that gives rise to the lexicon, such as reinforcement learning dynamics, here in this approach, usually the dynamics is underspecified. So the characterization is kind of at the population level, at a fixed point, rather than actually modeling the dynamics of communication. And of course, there are some exceptions to all of this, but the approach I would like to present in this talk today is actually integrating these two approaches. So basically combining utility maximization with informational constraints, and basically the solution would be kind of a trade-off that has both parts in it. And similar to the previous talk, I'll focus specifically on the idea of efficient compression as our notion for informational constraints, and I'll argue that this principle can explain how humans communicate and reason about meaning. So in the first part of the first talk, I showed you how this applies to pragmatic reasoning. In this talk, I'll show how it applies to semantics, also to the emergence of the lexicon, and I will also argue that it can guide artificial agents towards more human-like communication. But now you may wonder, well, you've all probably heard about large language models like ChatGPT, which are extremely impressive. So is this problem already solved? Do we actually need this? And so the answer is Yeah, well, large language models are indeed very impressive. They're also limited in several important ways. So first of all, they're not grounded in the way we perceive and act in the world. They also require huge amounts of training data that are available mainly in English, not so much in other languages. So if you want to understand something fundamental about language, this is a limitation. And most importantly, they don't tell us why languages are structured the way they are and how did they evolve to be that way. They just kind of give us a really good snapshot of language as it is based on the training data they have. And so what I would like to argue that is that the approach I'll present in this talk could help address these challenges.
Can you say just a bit more about what you mean by a large language model not being grounded?
Yeah, so these models are trained only on text. They're not trained on vision, on motor control, on all the things we take for granted in our interaction in the world, which we don't necessarily talk about. Sometimes we do, sometimes we don't. So they're only based on text. It's really impressive how much they can do just based on that. But to me, it's a finding more about language, that our language encodes so much about the world rather than something about the models, these models. That's a different story. Okay, so what I'll do next, I'll start by giving you a few examples of what we mean by semantic variation across languages and the kind of phenomena that we'd like to explain with our models. I'll then present the theoretical framework I'm using, which is mathematical theory of compression and its relation to the information bottleneck principle, which is very similar to the rate distortion framework I discussed in the previous talk. And then the third part of my talk, I'll show you the broad empirical evidence that we have that efficient compression underlies the evolution of the lexicon, and I'll conclude by showing how we could integrate this approach with utility maximization. And I'll show you some nice results that we have in that aspect. Okay, so let's start with semantic variation across languages, and specifically I'll focus here on the case of color naming, which is a unique case where we have large-scale naming data from over 100 languages across the world, so mainly from non-industrialized societies, which were collected in the 70s as part of a project called the World Color Survey. This was by Bill and Kay, and we also have here more recent color naming data from English, so one industrialized society is included here. So what you see here is a standard color naming grid, and participants or speakers of each language were asked to provide a name for each one of the colors that you see in this grid. So here is an example from the actual English data, and you can see that most of the participants use the word blue to describe this particular color chip, but some participants use also other terms. And when we kind of average the responses across participants, we get this distribution, which we call a naming distribution. So here are 4 languages, for example. For each language, you see the contour plot of its naming distribution. So, for example, this green blob here corresponds to a green category, and the reason I know it's a green category is because these colors are not arbitrary; they are the descent rate of the color category. And the white regions here corresponds to probabilities below 40%. Okay. So just by looking at these 4 languages, you can see that there is you can kind of get an impression of the wide variation across languages. So these languages vary not only in the number of categories, but also in their structure, right? But at the same time, there are also some patterns that are similar across all languages, right? For example, all of these languages have a sort of a reddish category. So we'd like kind of a theoretical framework that could explain all of these phenomena. And I'd like to emphasize that these phenomena are not only, they do not only appear in color naming. For example, if you look also at other domains like artifacts and specifically container naming. So this is a domain where we have data from Dutch and French native speakers with respect to kind of these kinds of container images. So as before, speakers were asked to provide a name for each one of these containers. take this one, for example. So this is the naming distribution of the Dutch for the Dutch participants, and this is the naming distribution for the French participants. And you can see that even though these two languages are closely related, they still exhibit different probabilistic naming patterns. So the question, how can we explain all of these phenomena that we see in the data? So one very influential approach to this problem is based on the idea of efficient communication, and I think it was captured very nicely by Eleanor Roche, also very intuitively in the late 90s, who argued that what one wishes to gain from one's categories is a great deal of information about the environment while conserving finite resources as much as possible. So this intuitive idea was formulated in many different ways and was applied not just to color naming, but also to other semantic domains, and also to many other aspects of language, actually. But when we look at this literature on efficient communication, it has largely left open three questions. First of all, as I mentioned before, there have been many different formulations of this idea of efficient communication, so it has been unclear whether there is an independently motivated principle of efficiency that can explain word meanings, or basically the structure of the lexicon across languages. We've also seen that semantic categories can have soft rather than hard boundaries, as I showed you in the contour plots, and so it seems unclear how efficient communication could explain that, because intuitively soft category boundaries in these regions, these white regions of low probability or inconsistent naming, they introduce ambiguity to communication and seem to pose a challenge for efficiency. So how to reconcile these two ideas has remained open. And finally, it has been largely unclear how drive for efficiency can shape language evolution. So what I will argue in this talk is that pressure for, or the mathematical theory of compression could help address these three open questions. So next, I'll present a basically theoretical framework and how it's related to the information balance principle, which I think, Rava, did you talk about IB? No?
Yeah, just mentioned.
Okay, so I'll explain it a little bit in more detail. And then we'll talk about the empirical evidence and the integrated framework. So even though I'll focus on color naming as a running example for simplicity, by now we have converging evidence from hundreds of languages and multiple semantic domains, and I'll briefly present all of these evidence towards the end of this part, but I'll use color naming as kind of a running example simply because it's the most kind of elaborated domain that we have. So the main idea is that efficient compression under limited resources underlies the ability to communicate and reason about meaning, and in our case, we'll use the information bottleneck to instantiate this idea. So information bottleneck principle is a very general information theoretic principle that was introduced by Tishby et al. In 1999. It has large scope, especially in machine learning, but also in computational neuroscience, and it can derive directly from rate distortion theory, and this will show you next. But before I kind of dive into all of these technical details, I'd like to give you kind of the high-level intuition. So we can think about the information bottleneck principle as a trade-off between complexity and accuracy of the lexicon. So every language can be mapped to a point on this plane. And this plane is divided into two regions. The region above the black curve is unachievable, which means that there are no languages can lie there. Actual languages can lie either on the curve or below it. And the black curve itself is the theoretical limit of efficiency that is defined by the set of optimal information bottleneck systems. So if we only care about minimizing complexity, we get a system here at the origin where all colors are mapped to a single category. And as we increase complexity, we get more refined systems. They're all still optimal in the sense that they achieve the maximal possible accuracy for their level of complexity. And at the very high end here, we get a system that is maximally complex, but also maximally accurate, in which basically every color is mapped to its own category. And what I'll show you is that we can take actual languages in our data and map them onto to points along this theoretical limit. So to define this precisely, let's start with a simple communication model, which is very similar to the communication model that we had in the previous talk. And so again, we have a speaker and a listener. Speaker is defined by an encoder, the listener is defined by a decoder, and here we wish to focus mainly on the encoder, right, which is analogous to the naming distribution. While in the previous talk, we actually focused more on the decoder. So now we'll assume, basically, for simplicity, that the listener is doing Bayesian inference with respect to the speaker. But this is actually not a required assumption. We can actually relax it and get the same results. But I'm assuming it just for kind of simplicity here. The more important assumption that we'll make is that the communication is not about arbitrary messages, but rather that the speaker and listener are trying to communicate over a shared environment. And therefore, we'd like to ground this communication model in their shared representations of the environment. So we define these mental representations, M and M hat, as probability distributions over a set of features in the environment, set of relevant features, which are denoted here by U. So for example, in the case of color naming, or in the case of colors, we can use a standard perceptual space, which is called CLAP, which is this three-dimensional space that you see here, in order to ground this communication model in human-like color perception. And so the speaker mentally represents color by distribution over this three-dimensional space, and then the listener's task is to reconstruct the speaker's mental representation. So how this will work, the speaker observes color, mentally represents it as a probability distribution over this perceptual space. We assume that these distributions are Gaussians. Then it produces a word in order to communicate this mental representation of color, and then the listener receives the word W and tries to reconstruct the representation. But these, of course, could be mental representations of other things like containers, not necessarily colors. In these cases, for example, we can define these mental representations by using non-linguistic similarity judgments or visual features that are derived from state-of-the-art deep learning models. And these are things that we've done in other domains. So in order to instantiate this communication model, we basically need to specify two things. First is the underlying representation of the domain that determines the structure of these mental representations, and M hat, which are the messages that are being communicated here. And we also need to define a new distribution or a source distribution in kind of our rate distortion terminology, which is a prior distribution over meanings. And so estimating this prior distribution is actually a challenging problem on its own, which we have some work on that, but I don't want to dive into the details here. So for now, let's just assume that we have a reasonable method for estimating this prior distribution and that it's given to us. And now, once we've instantiated this communication model, we can ask, as before, what would be the optimal, what is an optimal semantic system, or what would be the optimal encoder in this case? So, as we discussed in the previous talk, if we take kind of a rate distortion theory approach, then according to this view, the speaker and listener should jointly optimize a trade-off between minimizing distortion or equivalently maximizing utility, or in this case we'll use accuracy, but it doesn't really matter, this is equivalent, and minimizing the complexity of the communication. So only maximizing utility or accuracy can lead to very complex communication system that requires basically very high precision, which amounts to high cognitive effort in terms of maintaining the lexicon, and therefore we also want, or if the speaker and listener are willing to tolerate some errors, then they should also try to minimize the complexity of their communication, which again, as before, is measured by the mutual information between speakers' meanings and words.
Can I ask you, so I missed the grounding. So the grounding, I guess, is the joint distribution between M and M.
No.
How do you implement the grounding?
specified probability distribution. So basically, it's like this communication model. It's like we're communicating belief states. I have some belief about the world, say a distribution over, say, colors, and I'm trying to communicate this belief to you. So the grounding is in the structure of M and M hat. And we define this probability distribution in, for example, in the case of color, by by assuming that the speaker represents each color as a Gaussian distribution over a perceptual space. And I should have mentioned that this perceptual space was designed such that small Euclidean differences between colors are correlated with perceptual dissimilarities. This is why we do questions.
So each M is a distribution.
Yes.
And then I have a prior over each distribution.
Exactly.
And the prior is the same for M and M.
The prior is the same for M, and M hat, the distribution of M hat will depend on the speakers and listeners behavior. Yeah? It might be clearer in a few slides.
Am I right that if you look across societies from this point of view, that they differ in their prior distributions? So the reason,
Absolutely.
and
Yes.
but that's the explanation for why out
There are differences?
in the U.S. we have a different lexicon for colors than in, say, Peru.
So I would argue that that's not the key explanation. So I'm making here a simplifying assumption that the prior over meanings is universal. It is shared across all languages. This is definitely a simplifying assumption. You're absolutely right.
But how else would you explain the difference across societies?
Using a single parameter, single trade-off parameter between, it's a kind of spoiler, between the complexity and accuracy. So there will be one parameter that can explain much of the cross-language variation that we see in the data with a shared universal prior, which is why I think that even though there are probably differences in the prior distribution, and there's a lot to study there, and it's a fascinating question on its own, trying to model that component, I think that it's probably not the key component for explaining cross-language variation, because we can explain much of the data across many domains. This is true for all of the domains I'll present here, and across hundreds of languages, we can explain them using a single parameter.
So I live in a society where there's a lot of ice,
Mm-hmm.
a lot of whites.
Yes.
Then I'm going to need to distinguish between a lot of different whites.
Yes.
And that's the accuracy.
Yeah, so you might operate at a higher trade-off for accuracy than other societies that don't care so much about color.
But shouldn't your theory predict which particular colors we distinguish
Yeah.
among?
Yeah, so this,
Whites as opposed to.
yeah, maybe I have, yeah, so let's see if I have,
It also depends on like what kind of poisonous plants, not on their frequency, but
I don't have
green
this,
may be important in some natural environments, but not in others. So the utility is
so you really have a backup slide that kind of shows the interaction between the prior and the perceptual space. I don't have it here, so I can show it afterwards if you want. But basically, in this case, the perceptual space does a lot of the work in determining which colors are more important. You see it has kind of an irregular structure, and like the exact connection and how it kind of both influences the results will probably be clear in a couple of slides. But basically, I am using a non-uniform prior that was estimated in a data-driven way, so it's not kind of an arbitrary uniform prior, but it is shared across all languages in this model. And the perceptual structure is also shared across all of them. So this is why we get kind of the irregularity in this in the perceptual space and the kind of non-uniformities in the prior inputs to the model, and they each kind of basically determine the entire set of solutions. Where each language falls along the kind of frontier depends on the trade-off in which the language operates in. But I think all of this will be much clearer in a few slides. Okay, so this is rate distortion theory. Same as before, very similar to what we had in the case of pragmatics. But the problem with rate distortion theory is it doesn't tell us how to choose the distortion measure or what should be the right utility or accuracy function. And this is where the information bottleneck principle comes into play. So recall that we defined these two messages, M and M hat, as mental representations or probabilities over some relevant features in the world, and therefore a natural distortion measure between them is the Keil divergence. And this is the exact distortion measure that is used in the information bottleneck principle, and we can show that the expected distortion equals some constant minus the second informational term between the speaker's words and the relevant features in the world. And so we can take this, so I should say, minimizing distortion amounts to maximizing this informational term, and so we can take it to be our accuracy term, and therefore, according to the information bottleneck principle, optimal languages or optimal semantic systems, these encoders, should minimize this trade-off between minimizing complexity, the mutual information between M and W, and maximizing accuracy, the mutual information between words and relevant features, for some trade-off beta between these two competing objectives. This trade-off beta will be a key parameter in this model. Okay, so now that we've kind of defined this hypothesis precisely, before we actually test this on actual data, we can derive from it two theoretical predictions, right? So if languages are indeed optimized to or evolve to optimize the information bottleneck principle, then we'd expect them to lie near the curve, right? So the distance between the complexity and accuracy of the language and the curve should be small. But not only that, if you look at the full naming distribution, or in this case the color naming distribution, and the encoder, the nearest encoder, optimal encoder along the curve, then we'd expect that these two systems would be similar to each other, or their dissimilarity would be small. So these two predictions are quantitative predictions that we can actually measure, test and measure. And here are the quantitative results, and you can see that inefficiency and dissimilarity both are small. Yeah.
Just to clarify questions, when you measure complexity, so every word that somebody mentions in the data, you add it to the
Yes.
So even if it appears just once,
Yes.
and then you just look at the bits in terms of the total number of words that have meaning over the data.
And then I estimate a naming distribution, so I average them. This is why low frequency words don't have a large effect. And then I plug them in the formula for mutual information.
But that's for the accuracy, but for the complexity?
So these are two informational terms.
I see.
So the complexity depends only on the naming distribution or only on the encoder, and the accuracy depends also on the how we define the structure of the mental representations or the probability distributions because of the Keil divergence there.
Second clarifying question, the picture before that you drew suggested that the scalar Gaussian, is that a scalar Gaussian?
No, it's a three-dimensional. Yeah, just for simplicity. Yeah, it's a three-dimensional Gaussian.
Like yellow, red, blue? I mean, what are the 3 dimensions?
Oh, what were the 3 dimensions? So these are 3 perceptual dimensions. I'll show. So the y-axis corresponds to lightness, and then hue and saturation are encoded in the orthogonal space.
Use the same model for continuous, so what would be the...
So that's actually a big question. I've compared several approaches. The best one is to ground, so instead of to ground the mental representations in non-linguistic human similarity judgments. So instead of kind of a space with Euclidean distance, we can think about a space where kind of elicits non-linguistic judgments or similarity judgments from participants and construct kind of a representational, underlying representational space. I also try to leverage state-of-the-art deep learning models in order to derive these kinds of representations. And some models actually perform very well and nearly as well as the human similarity judgments model, but still not as well. So there's some gap there to close. But yeah, this is an important question: how to ground this model in the right representation. So color is a case where we have this nice perceptual space, and this problem is can avoid it. But you're absolutely right. That's something to pay attention to. Okay, so these are the two theoretical predictions. These are quantitative results. And you can see that, so we want inefficiency and dissimilarity to be small. Both of them are small for our IB model, and small with respect to what. So to get a better sense of that, I've compared this model to a baseline model that was proposed in prior literature, where all of the components of the communication model are exactly the same, and the only difference is the way we define the notion of optimality or efficiency. So the fact that we gain, like the improvement that we see here in the results is only due to the fact that we grounded our notion of efficiency in an independently motivated principle, the information block principle. And so these quantitative results are nice and encouraging, but I think it's much more convincing to actually look at the data. So here are all of our languages plotted on this information plane, and you can see that indeed all of the languages in our data lie very close to the theoretical bound. And interestingly, they're spread along the steepest region of the curve, where every extra bit in complexity gives you relatively high gain in accuracy. Now, in order to kind of get a better sense of the actual similarity between the human languages and the optimal ones along the curve, let's go back to the 4 languages I showed you at the beginning. And here are the corresponding optimal systems along the curve, and you can see that the optimal systems capture much of the structure that we see in the data, including these white regions, right, that we also see in the model, which provides a theoretical explanation for why inconsistent naming or low agreement among speakers can be efficient for communication. Basically, it shows us that these phenomena can help achieve better compression, and therefore more efficient representation and communication of, at least for this domain. And this, yeah.
I have a basic misunderstanding. Colleen, it doesn't seem to be a blue category.
Mm-hmm.
How
Also in the model.
How can that get away without blue?
Oh, in terms of, they don't need it.
Really?
So basically, blue, they have a single term for blue, green, black, brown, this kind of a large category. So like they don't distinguish, they don't make distinctions between all of these colors, basically.
This is a tribal language?
It's from non-industrialized society in Peru and Brazil.
Not Portuguese, no Spanish.
So, no. There could be cases of contact, language contact, but I don't have knowledge about that in these data. I'll talk about this a little bit more later on. Yeah.
I would have thought just to talk about the sky, it would be useful to distinguish between a blue sky and
If they live on the forest, they never see this.
There's a book by the linguist Deutsche, and I think I remember that he said that blue is something, for example, you can't find in the Bible, that when they refer to the sky or the sea, they don't use blue, they use other colors, if my recollection is correct, so it's consistent with them. So it's not such an obvious color in the system.
there's also something a little bit counterintuitive when you think about it, which is colors that are abundant in our environment are not necessarily most useful for communication, right? If you have lots of greens and blues around you, you're probably not communicating about them. You're probably communicating more about the colors that are rare and correspond to important objects that kind of attract your attention. So we've seen that. One of the priors that I've tested was derived from kind of image statistics, and we've seen it there very clearly that statistics of the environment is actually not a good predictor, whereas other priors that are derived from kind of more social or linguistic data, not these data, actually account better for these data. But that's a topic for a different topic. So at this point, I'd like to emphasize that all of the components are fixed of the model are fixed across languages, and the only thing that varies is a single parameter beta that explains much of the cross-language variation that we see, as I mentioned before. Okay, so I've addressed these two open questions, but how does all of this relate to language evolution? So one of the most influential ideas in this context, especially in color naming, was proposed by Berlin and Kay in '69, who argued that color naming systems evolve by following this kind of discrete sequence of stages where at each stage another color category or another color term is added to the system. However, others have argued that color categories actually emerge more gradually. Often new categories emerge in regions of color space which were previously inconsistently named, so these white regions. And what I'll show you next is that by looking at how the optimal systems evolve as we gradually increase beta, we get an annealing process that basically synthesizes both of these approaches. So I'll show this with a movie. On the left, you'll see the same information plane as before, and all the languages in our data are now kind of in light blue, and there will be a red dot that will travel along the optimal frontier, and on the right you'll see the optimal information funneling system that corresponds to the red dot. You can see that at the beginning there are only two categories, and gradually new categories emerge. This is a continuous process, but there are also critical points along the way where a new category emerges. And this happens often in these white regions of inconsistent naming. At some point it becomes too refined, but this is okay, it's far from where actual languages lie. I don't know who is first.
So a thing that strikes me as obviously different from Berlin and Kay is that in this movie, the yellow region emerges sooner than red.
Right.
And in human languages, we don't observe any of the human languages that have yellow but not red.
Right. So so this is the main discrepancy of them all. I should say two things. First of all, there are pretty only few languages. So like the origin there is, I'm not sure how empirically supported the exact sequence at the beginning is. But regardless of that, even the languages which have red before yellow are still near optimal. And in a non-trivial way. So we control that. For each language, we constructed a set of hypothetical systems by doing several things like a rotation of the system or kind of sampling random Gaussian blobs. And in all of these cases, the actual languages, even those three-term languages with red instead of yellow, are more efficient than their hypothetical systems. So they're kind of locally optimal within these sets of hypothetical systems. So even if that's a discrepancy of them, like that's definitely a discrepancy of them all, but even with that, it seems that the model can explain or successfully predict the efficiency of the system.
Before, when you compare the traditional model to these four specific languages, did you fix beta or you just picked the beta that the estimation of the complexity gave you the closest point on the curve?
Yeah, so I fit beta. But to using only two numbers, not using the entire mean distribution, but basically I'm doing kind of picking the beta that is correspond to the nearest point along the curve. So So it's fitting in on the two-dimensional plane, not in the high-dimensional space of encoders. Okay. So now we can kind of take this this kind of trajectory that I showed you in this movie and summarize it in this bifurcation diagram, where each curve here corresponds to a category, and the color corresponds to the centroid of the category, and the width corresponds to the weight within the system. So each system is basically a slice here with a fixed complexity. And you can see that as complexity increases, or we gradually increase beta, that's equivalent, you can see that the categories kind of gradually change. Both their color changes a little bit, their weight, but also there are critical points where a new category or the number of categories changes. And what we can do now is to take the actual languages in our data and map them onto this theoretically derived evolutionary trajectory for color category evolution. So a natural conclusion from this is that languages evolve under pressure to optimize the information bottleneck principle. But what I've showed you so far is based only on data from a specific set of languages at a specific point in time. In order to directly test this prediction, we need what we call diachronic data, so data from at least one language, but at different points in time. Now, obtaining such data is generally hard, but luckily I was able to collaborate with Carrie Garvin, who has done fieldwork in Western Africa, in Ghana, a few years ago, and collected new color naming data for one language, Nafanra, for which we also had color naming data in the original World Color Survey, so from 1978. So now we have one language with data from 2 points in time, and we can test directly the prediction of this theory. So here's where the language was in 1978, and you can see that this is a great response to you, Mike. Even though it's a 3-term language without yellow, it lies very close to the theoretical bound. And the question is, did it remain near optimal over 40 years? So is the new data also lies near the bound? And the answer is yes. So here's the new system, the 2018 system, and you can see that this language has changed a lot over the past 40 years, probably due to contact with languages, with English and maybe other local languages there. But if you look at it carefully, it's actually different from English. So first of all, English lies here, so they don't lie at the same place. And also, for example, in this, in the FONRA of 2018, in this system, there's no pink or orange category, which we do have in English. So the system did not just copy the English system. It may have been pressured by English to kind of travel to a higher complexity solution, but it's not just a copy of the English system. But now you may wonder, well, maybe this is still trivial. Maybe if you start near the curve, then over time you'll still remain near the curve. And so to kind of address this potential concern, I've simulated a hypothetical process of language change, yes. That's exactly what I'm arguing.
But that wouldn't happen by just being exposed to other systems. It must be something about incentives that change.
Yeah, because there potentially, we don't have the right definition for that, but one potential explanation is that their accuracy demands became higher because English has higher accuracy.
Because they need to communicate with other people often.
Yeah.
Do I understand you correctly that in 1978, all colors were lumped either to orange or to brown?
There's also white.
And
So
white.
3 terms. Yeah. This is not the only language that has this structure. There are languages in the data that have only 3 terms. I showed it.
It's a certain isolated tribe or what?
A lot of these languages tend to be in Western Africa. I don't think it's necessarily, as far as I know, they're not isolated. But some languages, I showed it also in the 4 examples I showed, there was, where was it? Here, right? So there are languages with 4 color terms, and it goes all the way to, English, which is relatively more complex. There are also languages that are more complex than English. Yeah. So basically, the theoretical explanation according to this framework is that all languages are efficient, they're all near optimal, but if you don't need to communicate about color too much, you don't need it in your everyday interaction, then you want to be at a lower complexity. And in industrialized societies, for example, where a lot of objects are differentiated only based on their colors, then you might need more color terms, and then you're still kind of relatively near the curve, and which is starting to deviate a little bit, simply because it's just harder to be near the curve as you climb up. But you're still kind of, you maintain the level of complexity of an accuracy that you need, not more than that. Okay, so just to make sure that this result is not trivial, I've also simulated a hypothetical process of language change where we allow categories to kind of randomly drift and emerge over time. Basically, each category is formulated as a Gaussian, and we do a random walk on the parameters of these Gaussians. So you can see the green trajectory here is one example of such a hypothetical future trajectory. The gray region here corresponds to the region occupied by 50 hypothetical trajectories like that. All of them were initialized near the 1978 system, and you can see that they all diverge away from the curve and don't reach the 2018 system, which suggests that this result would have been unlikely to be observed if there wasn't actual pressure for efficiency that influenced how this language has changed over time. And I'm not saying efficiency is the only pressure that was involved here, but just that it's one important pressure. Yeah.
Are there any languages that you do see more standard curve?
Yeah.
Because
So.
that seems harder to justify intuitively. You can imagine once people have words that need particular colours that they didn't previously have, and it's more difficult to lose those words.
So colors tends to be a domain where empirically we tend to see that the color lexicon becomes richer. In theory, however, you can definitely think of domains where the lexicon will become actually smaller, more coarse. For example, there are tools that we don't need anymore, right? Fax machine. So we also lose words in language. So this basically depends on again, the trade-off, right? If some domain becomes less important, then beta for that domain will decrease over time. That's kind of a prediction of this.
You said that as language becomes more complex, it's harder for it to be on the frontier.
Yeah.
What is the argument there?
I mean, in terms of learnability results, we know it's harder to kind of estimate the points that are higher here, and it's basically based on my intuition. Besides these learnability results, which are related to this, basically you have a larger lexicon. It's harder to coordinate, and therefore there could be more discrepancies within the population that are kind of pulling it from the optimum.
So it's not in the model as
No,
it
no, no.
exists.
No, it's just my intuition. I should have been more explicit about it.
Do you take account of the fact that colors, in important sense, is really two-dimensional, in the sense that we have dark and bright shades?
Three-dimensional.
Yeah, we use that quite a bit.
Uh-huh.
So, we might not need that many words for brown, because we could say dark brown,
Yes.
and bright brown, and so forth.
Yeah. Right. So you could, or like blue, you can modify all of the color categories, but this framework here I don't consider that, because the idea here is that colors, or more generally objects in the world for which we have a single word, they have some privileged status for us, right? We don't have a single word for everything. So if we do have it, it means that this object has some privileged status, and we want to understand why. Why we have words for some colors and not for others, single words.
Yes, but I think that your distribution of the single words is affected by the fact that we have this additional way of description by dog.
Absolutely. I mean, it's like all of this is like taking language, which is a hugely complex thing with a lot of, there's compositionality, not just color, right? There's grammar. There's a lot of aspects of language that are not taken into account and definitely influence everything. So I'm kind of looking at a narrow slice of this thing called language and trying to explain it. And I'm making a lot of oversimplifying assumptions, and yet we can explain the data pretty well. So
the other thing I wanted to ask you, you take a model which, is more complicated than an alternative model. You think about the distribution that you want to make. Suppose you were, I don't know, suppose you were just, for instance, thinking about the partition, measuring the complexity by the number of cells in the partition.
yes.
You get similar results?
So first of all, look at this, right? This is soft clustering. All of the languages we see in the data, you see these these are level sets of the name distribution, right? So you see that the categories have probabilistic structure. You want to account for that. So if you just look at the partition, you lose a lot of the structure in the data that this model can capture very nicely. So this is one thing. And a lot of modeling work before this have indeed focused only on hard partitions. And in my view, it misses a lot of the important structure, not only in terms of explaining the data, but also explaining transitions. Because if you have partitions, then transitions are discrete. But if you kind of look at soft clustering, then you can think about a continuum here and smoothly kind of navigate it.
Hi, I'm just wondering how does bilingualism come into play in this? Could the drift between languages be correlated?
Yeah. So this is kind of a population level view. One of the kind of exciting future directions I have in mind is actually modeling different communication between different subpopulations, but this is future work, not something that I've already done.
Also, am I correct that this point for English is 1978 English?
No, English is more recent. It's 2014, I think.
Oh, okay.
Yeah. So it's not part of the World Color Survey is only, all of these great points are languages from non-industrialized societies from the World Color Survey, and we also have English.
And do you know is some evolution in English also?
Yes. So there is some evidence that there are emerging categories also in English. So for example, peach has become kind of, or teal. When you look at even more recent English naming data, you see that they become more kind of present and dominant categories where they weren't like that several decades ago. So there's definitely signs of continuous evolution, which is also a nice thing about here, which we don't have in Berlin and K, for example, where Berlin and K's approach is purely descriptive. Look at the data, you try to kind of infer a sequence. It is a predictive model, not a descriptive model, so we can make predictions of how languages will continue to evolve even if we haven't seen any data to support it.
Okay, so evolution of languages is not just convergence to more old like English, it's even in the most complex one still continues.
Could be, yeah. Yeah, definitely. Yeah.
So earlier you were discussing the evolution of the language in Africa as a result of being put in contact with English. What are the reasons why English is evolving?
Yeah.
Contact with other languages or what?
It could be. That's a great question. The truth is that I don't know. I can speculate that it's, our environment is changing. Right? We have not just in color, right? We constantly create new words to describe new, technological developments and other kinds of development. Like our world is changing. We need our language to, follow.
I was just wondering, so some societies have begun trading a lot, and historically some societies were at the center of trade hubs. So in some sense they have the exposure to the different kinds of objects that different people use, different societies use. But at the same time their own language may not have the words for certain kinds of colors that are in these objects that are being traded. I'm wondering if in this plot of all the languages of non-industrialized societies, historically, if we were to isolate some trade hubs and see what sort of complexity they have, in comparison to the complexity of the society, the language of the society to whom they're trading.
I'm not sure if we have enough data, like enough data for the interaction between subpopulation to actually do what you're suggesting. I think that would be interesting to look at. Yeah. Okay. So now I've addressed these three open questions, but of course the theoretical framework represented is not specific to color. And indeed, we've, together with my collaborators, we've tested the same theoretical approach across hundreds of languages and several semantic domains. So in all of these cases, we basically computed the information bound, theoretical bound, using the exact same method I mentioned before, compared us with cross-linguistic data, and found converging evidence for this theoretical framework.
Question about this: these theoretical curves look different because the priors are different, or
Priors and the underlying representation of the environment. So color is kind of a unique case where it's clear what to do. But yeah, in other cases, especially pronouns and pairs, I've actually compared, kind of done hypothesis testing for the underlying space to validate it, and kind of compare different approaches. So this basically suggests that efficient compression shapes the evolution of the lexicon across languages and across multiple semantic domains.
So what is the number for that? Is that probability?
No, it's like singular, plural. Okay. Yeah. Okay. So this kind of broad empirical evidence is very encouraging, but it doesn't take into account two things, right? It doesn't take into account utility, right? What we are trying to communicate for, only communicative success, basically. And it doesn't explicitly tell us how languages or population of interactive agents can kind of converge to solution along the frontier. And this brings me to the last part of my talk, where I'll basically propose kind of a new approach that integrates what I've just showed you with the idea of learning to coordinate communication protocol by utility maximization. As I mentioned at the beginning, this kind of the general approach, and kind of to start formalizing this, let's go back to the communication model, and we'll make two simple adjustments. Well, first of all, we'll explicitly formulate an observation that the speaker receives, this is not a main difference. It was there implicitly all the time, but this is the key difference. We'll also implicitly model a downstream action or that the listener needs to take based on the inference, based on the communication. So there's also not only kind of a notion of successful communication, but also a notion of a downstream task that the speaker and listener need to kind of satisfy or solve together. Now the kind of the integrative approach that I'm proposing is basically, instead of optimizing only the informational balance principle, we'll look at a trade-off between utility, which is defined by the expected utility, which is defined basically it's a function of the observation and the action, and then the complexity, the same complexity term as in information bottleneck principle or rate distortion, and this is the IB distortion, which is equivalent, minimizing this is equivalent to maximizing accuracy, but in this formulation it will actually be easier for us to think about distortion rather than informativeness or accuracy, just mathematically easier. So now we have this three-term objective function, which basically spans, we can think about the solution space in terms of this simplex, right, where if we look at each one of the extremes, right, so if we look only on maximizing utility, then we'll get solutions that are very task-specific. So they could be very good for one task, but they will have very weak generalization to other tasks. So if you want to kind of develop a notion of blue that could be useful both in the case where the task is to navigate to a blue landmark and to pick up a blue object. And we want to have this shared concept across tasks, and we won't get it, or won't necessarily get it in this extreme. Similarly, if the other two extremes are also kind of intuitively non-human-like, so if you only want to maximize accuracy, then we'll get systems, communication systems that are very complex and don't take into account any task that you may want to fulfill. So we may have concepts or words for things that are completely useless for everyday lives. And if you only want to minimize complexity, then we'll basically get no communication at all. So this kind of region in the middle is where we expect that, human-like semantic systems may emerge. So we kind of want to explore this trade-off, but not necessarily in the extremes, but actually all trade-off parameters should have some non-trivial weight. Okay, so now the question is, how do we solve this optimization problem? And it's particularly if you want to solve this at scale, right? Then this becomes kind of intractable, like rate distortion theory and information bottleneck. It's the same problem. If you want to do this at scale, then we need to use some variational methods. So one kind of natural variational methods to use is a variational information bottleneck. I don't know, probably haven't heard about it, but basically it defines a bound on this objective function and optimizes that bound with respect to a parametric distribution for the speaker and listener. That's kind of a very high-level description of that. But the limitation of this method is that it basically it was designed for continuous representations. And here in language, and especially in the case of words, we want discrete representations rather than continuous. So this VIB is not really helping us solve this problem in the way we want to achieve the solution. Another method that was proposed in the literature is called VQVAE, Vector Quantized Variational Autoencoders. And this method is really nice because it learns discrete representations that are also embedded in a continuous space. So it resembles a little bit the idea of word embeddings in natural language processing. But the problem with this method is that it doesn't take into account any informational constraints, and it also doesn't allow stochastic encoders. It's very deterministic. And so what we propose in order to solve this is a method that we call vector quantized variational IB, or VQVIB in short, which basically combines ideas from both VIB and VQVIE. And it allows us to basically define agents that can learn discrete representations that are embedded in a continuous semantic space or embedding space, similar to the idea of word embedding. So then we can study not only the structure of the encoder, but also the structure of the embedding space like we have in natural language. So I won't go into kind of all the technical details. I'll just give kind of the high-level idea. This is kind of the underlying schematic description of the architecture for VQVIB. So first of all, we parameterize the agents by a neural network. So in this case, like in our simulation, we just use a simple feed-forward network, but you can use basically any parametric function that you want. And so the speaker's encoder is parameterized by a neural network, and so is the listener's decoder. And now we have not only a decoder but also an actuator, right? So the speaker produces both a reconstruction and an action. And for simplicity here, I'm assuming that the observations and the mental representations, X and M, are the same. But we can relax this. That's not a crucial assumption. Just simplifies the notation. And what VQVIB is doing is the speaker basically takes an input and produces a vector in the kind of semantic embedding space. And there is a trainable codebook of, say, K word embeddings. K can be very large, so it won't be limiting, which is basically quantized vectors in the space, which are learned, or kind of their parameters are adapted and changed throughout the kind of simulation here. So the speaker produces an intermediate vector Z in the same space, which is then quantized into one of these kind of embedding or codebook vectors, analogous to word embeddings. And then the listener receives the quantized vector, W, and tries to reconstruct the speaker's observation and take an action. So in the case of simple reference games, the action would be guess the correct target or pick the target from the correct target based on from a set of distractors, for example, and your reconstruction would be kind of reconstructing the rich representation of the actual target, which are two different things. But if we can also apply, and we have applied this approach not only to reference games but also to cases where the listener, for example, needs to navigate to somewhere. So the speaker sees the target but cannot move, and the listener does not see the target but can move, and so the game is basically communicating the target, and then the listener needs to navigate there, and so the action would be kind of a trajectory within some kind of space. So this is a case where kind of the distinction between utility and accuracy is kind of should be more clear. And so this whole thing is trained with respect to our integrated objective function, and there's kind of a variational bound here that I'm skipping for the sake of time. But basically, we train this thing in a multi-agent simulation environment, and now we can basically analyze this system that emerged through this method. So let's see what happens in a simple color reference game that corresponds to our to the same stimulus set that we saw before for the world color survey. So here's the information plane, same one that we had before, and our languages and the data are here also in blue. And you can see the yellow dots here are different systems that, emergent systems, that we obtained by simulating communication with VQVIB agents. And you can see that indeed VQVIB is able to approximate the theoretical bound pretty well, even though it was not trained with respect to the vanilla information bottleneck principle. It was just an approximation. But not only that, if we look at the kind of emergent VQVIB systems, so this is looking basically at the speaker's encoder, and we compare them to the actual human languages in our data, you can see that VQVIB systems are actually capturing quite nicely the languages that we see in the data. So we haven't lost anything in terms of explaining the kind of cross-linguistic variation that we see in the data, and we have gained a lot in terms of the ability of scaling this approach to more to larger domains and more richer settings. And finally, we can now with VQVIB, we can look not just at an encoder but also at the structure of the embedding space. So here it is for kind of the same 2 points, and you can see, so these are basically, this is a 2D PCA visualization of the high-dimensional communication vectors, and you can see that how that kind of the embedding spaces are perceptually grounded and contain meaningful information about the relationship between the meaning of the signals. So it's a little bit harder to see with low complexity, where there are only, so in this system there are only 4 terms, but here as we kind of increase complexity, you can see that the semantic embedding space starts to kind of reflect a hue circle, where black and white fall in between. So this kind of replicates somehow the structure of the perceptual space in an in an abstract semantic space. Okay, so this is these are the results for color, and color is a relatively simple domain, especially for kind of these kinds of methods. We really want to leverage this approach and apply it to much larger domains, and so we started doing it with another domain based on the many names data set. So this is still a simple reference game, and this data set contains 25,000 images of natural objects across 7 different kind of high-level domains, like furniture, vehicles, people, things like that, animals. And the nice thing about this data set is that it also contains fine-grained naming data, as opposed to many kind of data sets in vision and computer vision, where you have only very coarse labels. So we actually have kind of the same granularity, only for English, unfortunately, but same granularity that we have for the color naming data, we also have for this data set. And another nice thing here is that we can test this approach on out-of-domain distribution. So we can train the agents on a subset of the domains and test them on the held-out domains and see how well their communication system can transfer to new domains that they haven't seen during training. So here are the results for the out-of-domain inputs, and you can see that as kind of the value of having or increasing the weight of accuracy, basically encouraging agents to develop a shared understanding beyond the specific task of this game, has value in terms of out-of-distribution utility. So it kind of helps them achieve better generalization to other tasks, which is exactly what we predicted at the beginning. And these two, so this curve here is for VQVIB, and these 2 other curves are comparisons with other methods that were previously proposed in the literature, and you can see that VQVIB also outperforms them. And we adjusted these methods to also incorporate the same informational constraints, so this is why beta here applies to them too. So this is a nice kind of validation of this approach. And again, as before, we can now not only kind of look at quantitative measures, but also look at the structure of the embedding space in this case. So here it is for, I think we sampled only a few kind of images. And the labels here are basically we assign to each communication vector the label that was most frequently associated with the images that were mapped to that vector. So the labels here are not used for training in any way. This is kind of an emergent structure or emergent kind of word embedding structure in these multi-agent simulations that did not use these labels. And you can see, for example, that it also contains some meaningful structure about the domain. So there is a cluster here for kind of furniture, and a cluster here for food-related things. So just kind of, yeah.
So let me ask the high-level questions then on study details. So it seems like that in your work, selecting variables that the variation alpha encoder is developing have a natural interpretation. And machine learning are infamous for having selected variables which are difficult to
Yes.
interpret. So I'm asking, what work will make it interpretable in your work? So somehow something special about what you are doing that making variables in machine learning have natural meanings. They are human. What is it like that gives you?
So I think it's a combination of having this basically communication signals that are embedded in a continuous space, in a semantic space. So most emergent communication frameworks just use arbitrary symbols. without this grounding or without this embedding. So this is one thing that is kind of technical. The second thing is that I think is that we're using the right optimization principle for training. So it's a principle that, you know, I kind of, most of my talk was basically about motivating this principle. Why I think it's really capturing something meaningful about how humans communicate and how human languages evolve. So I think it's a combination of the two, having the right kind of architecture and having the right optimization principle. Okay, so with this I'll kind of summarize this talk. So I've showed you that efficient compression shapes semantic systems and their evolution, that the optimal systems are human-like and can evolve by annealing a single trade-off parameter, beta, and this parameter also accounts for much of the cross-language variation that we see, and that kind of these findings suggest an integrated approach to emergent communication by trading off utility, complexity, and accuracy, which gives us this kind of conceptual space of thinking about the kind of space of emergent languages and where we want to, where we want our agents to behave and learn. So that's it, and let me know if you have any further questions.
Could you work with the colors and estimate different societies, shuttle price, or complexity? Correlate that with socioeconomic status of those societies?
Yeah, this is like one of the things I've been planning to do. It's a little bit hard to.
Causality, correlation.
Yeah, like more directly, like I want to be able to predict beta before seeing the language, before fitting the language. So I want to kind of find a set of factors, like looking at the population and being able to predict beta would be very nice. We're not there yet, though.
But to do that, wouldn't you have to know something about the distribution of observations and also the distribution of action sets associated with those observations?
In order to predict beta?
Yeah, the accuracy that you need is going to depend on the problems that you face.
Right.
So the problems you face are given by the distribution of possible observations. To go back to your theoretical model, distribution of observations and the distribution of action sets associated with those.
Right.
If you know that those things, then you can calculate.
Yeah, but there's also, for example, social factors, right? Social utilities, cultural factors, contact, the amount of factors that could, there are many factors that could influence beta, and we don't know yet which factors are more relevant than others.
But if you take your theoretical model seriously,
I try to.
then you should be able to calculate data from the theoretical model if you know
The
the
observation.
distribution of X and the distribution of action sets. Isn't that right?
I'm not sure I see.
Can you go back to that
Sure.
slide?
You're talking about.
Solutions. Right. Well, that thing you're maximizing.
So here there are even two trade-off parameters, right? So this is even more complicated than the vanilla information bottleneck case where there's only one trade-off parameter.
Right, but how much weight you put on those second and third, well, those second and third terms is going to depend on the problems you face.
Right.
So if you know the problems you face, you should be able to. There's some underlying utility that we're trying to maximize.
Yeah.
Net costs. The problems you face are going to determine how you trade off accuracy and complexity.
but wouldn't that be potentially a complex function of the observations and actions? Like,
It could be
Yeah,
a complex function, but.
which I don't know the function.
But you could estimate that.
Yeah, okay, so I think we're on the same page.
Okay.
Yeah, yeah.
Are there any examples where utility is different than accuracy? It seems like in many
Yeah.
situations it's the same
Yeah,
thing.
so this is the example I mentioned with navigation. So for example, basically accuracy is how well the listener is able to reconstruct the speaker's mental representations. For example, if you have a task where the task is navigate to the red flag, okay, or there are several flags, the speaker sees the target, the target color, the listener does not see, but needs to navigate there. So for example, the communication could be just, let's communicate the color of the target, right, the landmark. And then there's just basically how well the listener is able to reconstruct the speaker's mental representation of color, whereas utility could be the distance from the target. So how well the listener actually navigated to the correct position. These kind of two different spaces. Examples.
I missed the first part, so please ignore if you already answered that. Just trying to understand the space of feasible complexity accuracy pairs. So you have the frontier. Not everything under the frontier is feasible.
That's true.
So, and you have this picture of the drift that
Right.
suggested that some space, it seems like it would be a very narrow band below the.
Yeah.
So can you tell us a bit more about that space of feasible pairs?
Yes.
Just to clarify, because something that is maximally complex is by your definition also perfectly accurate.
Okay, so
Because of the Bayesian updates.
right.
If you have infinite complexity, then you also have infinite perfect accuracy.
Right. So you're basically asking about points that are infeasible here.
Yes.
Absolutely. So there is a complementing problem which is called but basically it is doing that. Instead of maximizing the IB objective, we can try to instead of minimizing the IB objective, we try to maximize it. So it's a much harder problem in terms of characterizing it. I don't think there's kind of a clean analytical solution, but it is possible to do that numerically. And so and then there will be some bound here. You're absolutely right.
The drift that you simulated suggested that it would remain relatively close to the.
So the drift here depends also on a lot of the parameters of the drift. So for example, I determined the width of the Gaussians based on some kind of perceptual parameter that is derived from, psychophysics experiments. So there are also a lot of parameters that could determine the privacy funnel. That's the name of the complementing problem. But there are a lot of parameters that can determine the kind of the structure of the random drift. But you're right, like we can do a more thorough, careful exploration of the space. I've done that a little bit in other settings, not in this line of work. And I think there is at least one former student of Tally PHP who has done also some work on that. But yeah, this is basically what I know, that you're absolutely right, there is a bound here and not everything is achievable.
In terms of what we can measure to put actual languages on the graph, I guess for complexity, you show people color chips, you record the distribution of words they give, you look at the entropy of the distribution of words that are ever used. For accuracy, are you asking what an ideal observer could reconstruct?
Yes.
So it's
Simply because we don't have data. But we could, in theory, it's possible to collect data. It's just we don't have that in the world color survey.
so that would be interesting to do experiments where you ask someone in response to
and
words.
see if there's a match, if they're consistent or not. not immediately clear that it will be like.
Well, I guess the question is, would that allow you to separately measure accuracy and utility, for example?
Yes. Accuracy. Yes. Yeah.
And then plot things in three dimensions.
Yes. Yes. Any other questions?
Okay, thank you very much.
Thank you.